Hi guys, how are you? Let's have a little math discussion again today. We're going to talk about frequencies, and I've finally been able to make an animation for you, which I've been wanting to make for a very, very long time. So we're going to talk about how circlings explain frequency. And here's a little snapshot of an animation you're going to get in a second. So remember, here's the equation for the individual monad. It is Euler's equation over all possible radii and phases, right? Just as Hockney defined it. Which, with an update to the slide, which I just performed, is right here. For example, Hockney hyperreason. Imagine an infinite number of Euler circles radiating out from an origin which has zero frequency, zero amplitude, and zero phase. So that would be a point right in the middle here of this smallest one, an invisible point that's not there. Each of these circles has a different radius, amplitude, so that's all these going out, but no matter the radius, the Euler circle itself always balances to zero because the net sum of all these values around a circle balance to that infinitesimal non-existent point, which should have zero phase, zero amplitude, and zero property, zero frequency right in the very middle, yeah? All right, so each circling, right, is each one of these circles. And from building up a whole bunch of circlings, stacking them all on top of each other as an instance of all circlings, that's the monad. Okay, perfect. So let's go on and see what I have done with this now. So frequencies, so circling is this equation, and you expand that and you get that equation. Let's play this animation. So the speed of each of these points going around their respective circles is actually the exact same speed through numbers, on the ontological number grid of imaginary and real numbers, real and imaginary numbers. They travel through the number grid at the exact same speed. That's called the linear speed, or the tangential speed even. And I think in this animation it was like 10 pixels per frame or something. So just to prove that, yes, these points are all moving at the exact same speed through pixels. But that leads them to have different frequencies because this small radius circle has much less distance to go through. And having much less distance to go through, it completes its cycle, its period much more quickly, and that gives it a higher frequency. So you can see this outer large radius blue circle, blue frequency, blue circling, right? It has a very long, very gentle wave, right? Green is obviously the intermediate one here if you're not colorblind, and then red is the inner one, and it's going really, really fast because it has hardly any distance to travel around at all. So it's just going like crazy. So, I mean, you might think sometimes people might think, or I mean, it might seem intuitive to think that the larger amplitude wave should have more energy. However, that's not actually how it works in physics, in the physics of photons. The energy of a photon is given by h, which is a constant, Planck's constant, times its frequency. So the energy of a photon is proportional to its frequency and has nothing to do with a photon's amplitude. The energy, let me repeat again because it's so unexpected. It's really quite unexpected because, I mean, with a water wave, for example, a big water wave has a lot of energy. We all know that. Tiny water waves have almost no energy. But this is a case where it does not quite translate in a direct analogy for photons, for electromagnetic waves. The energy of an electromagnetic wave, a photon, its energy is proportional to its frequency and has no dependence on the photon's amplitude whatsoever. And it seems, in fact, that a photon's amplitude is in fact proportional to its frequency, so that it has a smaller amplitude for higher frequency. So that's just very interesting. Now, we kind of know that principle through radio, for example. So for radio waves, a radio wave, which is a big, long wave, can travel right across the city and goes around all the buildings. A radio wave is big enough, they're humongous. They can go right around a whole building, and that's how you can pick up your FM and AM radio within the city, because the waves are so big, they go right around the buildings and can still get to your antenna, right? But obviously, visible waves don't go around a building, they stop at the building. They're not big enough to get around a building, right? Obviously, if you go high enough energy, then the waves will just go right through, like a gamma ray, very, very small frequency, and is a very tiny particle then, very small radius then, and it's small enough, although energetic enough too, that it'll go right through a building, obviously, right? So anyway, just some interesting properties. Now, what I really like about this is that if the photon is a fundamental, is represented, or sorry, yeah, is a circling, basically. In the expanded form of the circling, where you have a real component and an imaginary component, and they're orthogonal to each other, I mean, you really just automatically have the setup here for describing a photon, which is a electric and magnetic wave component coupled together, oscillating together and traveling together. This equation automatically gives you a photon, and I would presume that it's the magnetic component, which is the imaginary numbered term, just because of some of the strange properties of imaginary numbers compared to real numbers. Imaginary numbers seem to be antisymmetric, which kind of corresponds more with the behavior of magnetism as opposed to electricity. Seems more symmetric, which is like cosine sort of valued, right? Being an even function. So I mean, that's a ready way to describe a photon. So it's just, I don't know, nice. Anyway, you can see that this, another way to think of it is this blue wave, this large radius, high amplitude, low frequency blue wave. It's just moving very slow, right? It's gentle. It's like laggard and gentle. This high frequency inner small radius, it's very highly agitated, right? Think of it in terms of agitation. It's very highly agitated. It's moving very, very quickly up and down on its cycle, has to get back and forth really, really, really quickly. And that's where its energy is coming from. That's why it has higher energy, because it's just shaking so quickly and so fast, right? Even though it's a small amplitude, it's still doing it really vigorously and really actively and energetically, right? So that's why it has high energy. And again, the blue wave is just slow and gentle, and that's why it has low energy, right? Okay, now one thing to talk about this is what we saw from Morg, in which he had actually gotten from, it looked like Stark was the one who wrote this. So, I mean, obviously these are all pseudonyms except for Morg, we know who that is, but obviously at some point somebody did something to Hockney and took over the stuff, and the new person wasn't quite as good as Hockney. And I mean, I call this amateurish. I mean, this is a really amateurish way to develop frequencies. I mean, it's cute, it's neat, you can see why they thought that, but it's really just not rational. And this equation to produce this sort of cycling, that's not based on Euler's formula. You don't get this behavior out of Euler's formula directly. With Euler's formula, simply with different radii, as I'm doing here, I mean, it's direct one-to-one correspondence. This is plotting Euler's formula just with different radii and a constant rate of speed, which corresponds with the speed of light or something related to the speed of light, and you automatically get your frequencies. This is some weird creation. Like, it's just, it just does not follow directly from Euler's equation at all. And you have to make up a new equation for it, and it's a bit amateurish. But you know, I don't want to make fun of people who don't know what they're doing, because you know, it was a good effort really for people, person who apparently, you know, didn't have much education in math or physics in high school and stuff like that. I mean, it's neat. It is amateurish, but I don't mean to make fun, because I mean, you're putting yourself out there trying to advance it, and you make a mistake, that happens. Anyway, I am quoted in one of their books asking as to why it seems like they don't know what they're doing sometimes, because this may have been started in one of the Hockney books, but it's definitely in a Stark book. So it's just it's not the correct approach. This is the correct approach right here, using Euler's formula exactly in the way that Hockney said to, which was an infinite number of Euler circles radiating out from an origin, right? Each of these has a different radius, which is an amplitude, and no matter the radius, the Euler circle itself balances to zero because they're all balanced on that point. So that's one-to-one correspondence here. Hockney and Hyperreason at the point of Hyperreason book was making sense. This makes sense. This is just taking the the unit circle and then applying the infinity multiplier. That's automatically what you get, and that's what these equations describe this paragraph here, and this simulation here is a simulation of these equations. So it's all one-to-one here, and then again, this as well, this is just doing the same thing, and I'm just showing you how you get, because I had a comment, as you recall, I covered comments a couple of videos ago or something, and someone was saying that, oh, I'm not doing this right, no, and Morg was doing it right. Well, I'm just demonstrating this is the correct way, and it does come straight from Hockney and straight from a direct application of Euler's formula. This is Euler's formula, you realize, right? E to the I something. That's always Euler's formula, so it's just applying Euler's formula. That's all it is. And it's showing you how you get the different frequencies. Nice. And how that corresponds with energy, helps us understand a photon. We have this real and imaginary component, which is just like analogous, must be related. I mean, this is physics to start doing, right? I said in the last video, you can start doing physics. This is applied ontological mathematical physics here, is figuring out, okay, of these two components, what's the electric component and what's the magnetic component? And I mean, this is basic stuff. I mean, this is like high school. Maybe, well, Euler's equation, I guess maybe that's a bit more first or second year university. These equations here, that's what's high school level. Yeah, the E equals H nu and blah, blah, blah. That's pretty much high school. Maybe a senior physics, or I think maybe today, because of grade inflation, this is actually now more found in first year university in physics rather than in high school. In my day, it was found still in high school. Yeah, anyway, so that's fun. That's neat. I just like looking at this. I guess I got nothing more to say about it, but I thought you would like this animation. Let me know, anyone, if you want this animation. I can make it available on a OneDrive link or something. Yeah, there you go. So if you want to support my work, again, obviously would really appreciate that. And there's my books. If you haven't read them, better read them. I mean, this is the most entertaining one, I would say, Planet Wars. This one is great, The Layman's Guide. I mean, that really just is pretty easy read and just lays out the case. But it's really backstory. These two books are really backstory to the full, just like, holy crap, what the hell is happening in the world that I write about in Planet Wars? And I'm just like I end The Layman's Guide with like, and it's kind of spooky because I'm like, it seems like something else is going on. And then I figure out what's going on, and I wrote about it in Planet Wars. I was like, holy shit, something is really going on, and it's pretty bad and pretty dangerous. And like, we gotta pay attention, and here's the proof. And here's how it comes from. Ontological mathematics has supported me through all the books. And anyway, really fun. And then, yeah, Luminism I'm going to write a second edition of one day. And then, yeah, this is more applied ontological mathematics, debunking the simultaneity paradox and solving the double slit experiment. Really easy to do, actually. Just need to change a reference frame. Yeah, maybe I should do more videos on that one day. Okay, all right. Have a good day, everyone. And bye-bye.